Bonjour à tous. Merci beaucoup pour l'invitation à cette conférence. Je suis très désolé. It's not possible for us to come today to Paris because we are in the midterm of the university and everyone is everywhere in the world. I'm actually not Helge Simon. I'm Michael Bruce. I'm the CEO of the Envimet company, and we worked close together on the project we are going to present today. And this is a project about the seed discard. So on the next slide. Okay, so what we actually do, we can keep this picture. So what we do is microclimate modeling. So we are analyzing the impacts of the built environment on the microclimate variables like solar radiation, wind flow, soil conditions, vegetation, pollutant dispersions. So this is a holistic model. What you see here is an overview of all the components which are included. And all these components are calculated in parallel. So there is always the feedback between, say, vegetation, evapotranspiration, air humidity, humidity at the walls, turbulence generated by buildings, and so on. So it's not an isolated system or a system where several systems go together, but it's all in one system, which makes it quite usable for showing the interactions that actually take place when we change little things. And most of the changes are little things in the urban environment. It's about few trees. It's about surface materials. It's about building the one building to the left or the other building to the right. So it's a high resolution model where we work with resolutions about 1 meter, 2 meters, 3 meters or so. And we normally also look at relatively small scales. So like the seed discard, about 500 to 600 square meters around what actually is going to be built or transposed or to be analyzed. Okay, next step maybe. So the model is particular, it's just now 20 years plus, so it's a relatively old model, but doesn't mean that it is old from the physics, so it's just being developed all through the time, the Envimet model. I think, or other people say that, I should not say that from ourselves, but we think it's one of the leading simulation systems we actually have worldwide. And it's used in about, I don't know, 95 countries, and we have about 8,000 registered users. So it's a big community, which actually comes from very different disciplines. So there are people coming from human health, interested in the pollutants. There are people from landscape architecture interested in the flow patterns around the vegetation. There are architects interested in the building energy performance. So it's a very colorful patchwork of different science that come together and different interests. And so that makes it really fascinating because we work together with so many different people having so many different views on sustainability, on resilience, and all these connected things like green cities, and especially in the framework of climate change, when we talk about the different measures we are going to take to, for example, to cool down the cities and cool down the heat waves that may come up. And in Paris, you also had a very severe heat wave in 2003, like we did, and is still in the heads, although it's for quite some time ago, and we can expect that these heat waves are going to increase over the next years in the impact of climate change. So that's a big thing today in urban planning, in architecture, and in landscape architecture. And we hope that with our model, as we see in the example here, we help a bit to quantify these effects, to say what is the effect of this, what is the effect of that, and we cannot implement everything, of course, but we can have a rule of thumb which will be the most effective thing. Okay, next slide, please. So we actually analyzed two meteorological scenarios in our study. The one was a very regular summer day like we have in this year, so average temperatures, not too hot, not too cold. And the second meteorological scenario we looked at was what happened in the same design, in the same architectural landscape, architectural situation on a summer heat stress day as it is predicted in a heat wave in the year maybe 2050. It could of course be 2051 or 5, that doesn't matter. So it's an IPCC heat stress day actually. And from the terms of the modeling, we have done actually 3 different scenarios. The first scenario is the status quo. So this is how the area of the seed discard looks today. And the second scenario we first looked at is the planning scenario. So what is going to be implemented in the recent plans? So what are the proposed changes in the scenario? This, of course, often changes a bit. So depending on what plan you got at what time you got the plans. So don't be too hard on it. So next slide, please. This is mitigation measures. So from the mitigation measures we have for interacting with the climate change and taking countermeasures, we actually used 3 different tools. The one was we made a small change in the urban design. This was very, very small. We placed additional vegetation, and we also took the freedom to change surface materials in the design and in the situation as it is today. And the target was that we want to quantify and evaluate which will be the effect of these redesign measures on the local microclimate and on the thermal stress. So next slide is urbanization of weather data. And another point where we also are very interested in right now is what you call the urbanization of weather data for the building energy system simulations. So that we of course know that each building which is included in a cluster of other buildings included in an urban framework has of course its own patterns of wind flow patterns on the different facades, is that it has its own impact of radiative transfer and also the air temperature and the humidity on the different sites and the forms of the buildings. That can vary a lot. And what we want, of course, to do to make a good building energy simulation, or better to provide better data for building energy simulations, so not just use an average climate data file which is valid for a complete urban area, but to really make a localization of the very specific location where this building is going to be or is at the moment. So that's the side effect of these microclimate simulations, because we get patterns of all these relevant microclimate variables, and we cannot not only use them to analyze the outside environment, the outdoor space, we can also use them to make a higher resolution modeling of the indoor space by providing the other models, other urban energy models with this urbanized building data. Okay, next slide, please. So this is a brief summary of the meteorological framework we used. So with EnviMet, we're usually calculating a day or 2 or 3. So we're not calculating a whole year. That's not possible because the model is too time consuming. So we normally pick a typical day with typical conditions and analyze these days under the different situations. Of course, we can have several simulations, say one for autumn, one for winter, one for a cold day, one for another day. So we used a wind with 1 meter per second, which is a relatively slow wind coming from the south-southwest. We did not use any cloud cover. And for the 2 scenarios we had for the regular summer day, we had an air temperature amplitude of 50 degrees centigrade in the morning and 30 degrees in the afternoon. And we had, for the hot day, we had a minimum of 80 degrees in the night and of 36 degrees in the day. And for the soil water, which is very important because when we use green infrastructure, trees and grass and so on, it's of course important that they do have water to evaporate and transpirate. So for the regular day, for the summer, we used 50% water. And for the hot scenario, 2050, we said we have only 30% of available soil water. So that would be a day within a longer lasting period of hot days or warm days, where we already get some shortage of water in the soil system. Okay, next slide, please. This is an overview about the model area we used. So the red buildings, actually, these are, according to the plans we had in that time, the new buildings that are supposed to be constructed on the campus area, while the gray ones and the trees, these are the existing environment. Okay, next slide, please. Thanks. So what you now here see, this is actually the transformation from the vector drawing from the last slide, and this is how it looks in our EnviMet model. So it's, of course, it's a grid model, so all these little curvatures and diagonal lines are getting a bit gritty. You see there's lots of vegetation. It's a very green area. We will see this in the simulation results as well. We have the big park area on the left side or on the western side, and we have really a huge amount of trees in the area at all. And on the right-hand side, you see the same model, but including the new buildings, and of course also the reduction of trees due to the construction of the new models, and also, of course, changes in the surfaces, because we need to have paths and roads to have access to these buildings. So these are basically based on the plans we did have, and where things were not that clear, we made we guessed as good as we could. Okay, next slide, please. Thanks. So this is just a small slide. This is a three-dimensional image just to give you an impression how it looks in this gridded model environment. Okay, next slide. So what you see here, this is a typical result when we analyze the microscale modeling. What you see here, this is a horizontal view of the area. The black boxes, these are the buildings. We do not show the vegetation right now because otherwise we were not able to see the temperature because everything will be green. And what we see here is a horizontal cut at the 1.8 meter level. So this is almost the reference level of 2 meters for the meteorological variables. And it's a level where the humans are actually most influenced by the local climate. And the temperature, the colors in this image, they represent the different air temperature we do have at noon. So that's 13 o'clock, so high noon. And you see there is a really large range of air temperature within this area. I mean, it's only 600 by 600 meters, but you also already have a range of 3.6 Kelvin from the coolest spot to the hottest spot. That's really a large range for such a small area. It's actually more or less the range you have between the center of Central Park in New York City and the hottest points in New York City. So that's just to give you an impression that this is really a large gradient in temperature. And this is basically due to the huge amount of green spaces we do have in that area in the situation today. Of course, because of the low wind speeds, because we selected a low wind day, so every temperature could stay in its place and develop clearly. And we have a lot of different surfaces. So for example, you see the roundabouts very well because they're completely unshaded and full of asphalt, and you see there are really hot spots in the domain. Okay, next slide, please. Okay, thanks, yeah. This is another view at the situation as it is today. What we see here is the surface temperature, actually. So the absolute value of the surface if we touch it. So if we touch the asphalt road, if we touch the soil below the trees, just to give you an impression what the range of these temperatures is and how much diversification is there in that area. We see the roads. You see the effects of the tree shade, so these are the little blue bubbles everywhere. And you see there's a large range, it's 24 kelvins between the hottest areas, which are in the roundabouts, especially those roundabouts which do not have a green center. And you see the large amount of trees that actually very effectively shade most of the surface area in the Parc de Butte and on the other side of the central road. So next slide, please. Okay, thanks. So this now is the scenario. So this is the same model, the same settings. It's again the summer day 2017, but now we have implemented the new buildings. We have removed the trees where the buildings are supposed to be and also added the additional road network. Everything else is the same. It's the same cut, it's the same time, and it's of course the same color scale. And you see just visually, of course, that there is a big change. So that there is still a cool area in the park, but the temperature distribution in the central parts of the campus has changed dramatically due to that intervention. Basically because we do have less trees now, more buildings, and also the buildings we have constructed along the road do act as a barrier which prevents that the cooler air from the park can penetrate more to the eastern parts of the area. So next slide, please. Thanks. So what you now see, this is another way of looking at it. It's a difference map. So we take the two results, status quo as it is today and the planning scenario, and we just subtract the two. So it's a more scientific way of seeing the changes. So just to say on the positive figures, so these are all the colors that are greeny to yellow, orange to purple. So these are the area where the situation, the air temperature now is hotter in the planning scenario. And the blue areas, these are the locations where actually things are a bit cooler in the planned scenario. So you see from the figure that we can have an increase up to 2.8 Kelvin of air temperature inside this cluster due to the buildings. And if you remember that we are trying to avoid 2.0 degrees change in the Paris commitment, and then we see that we have 2.8 degrees here, then you see that there's a lot of possibilities maybe how we can work with the designs to improve the climate conditions using the designs. We also have some areas where it is actually a bit cooler. So these are the green spots in the southern parts. This is basically due to changes in the wind speed. So because in the former time where no buildings have been placed there, some airflow from the road could penetrate in that area. The road was hot, and now the buildings changed the airflow a bit. So, but that's always the case that you also do the wind effects have also some changes in the positive direction. Yes, so next slide, please. Thank you. So this had been the air temperature, but there is also another way of looking at the microclimate conditions, and this is, of course, the thermal comfort. So just like in the indoor building physics, where you ask yourself, will a person be comfortable with the settings of the climate conditions or with the indoor air temperature? You can do the same for the outside, and it's basically the same principle. So you use the basic meteorological variables that influence the human sensation of heat. And this is basically the wind speed, the solar radiation, and in the infrared radiation. So the infrared radiation is of course important during the night, while in the solar radiation normally during the day. The air temperature, of course, and in extreme cases, the air humidity. So if you go to the tropical scenarios with 80%, 90% air humidity, of course, thermal discomfort can also be caused by the simple fact that we cannot sweat anymore. So there are different thermal comfort models. I think there are at least 20 or 30 different thermal comfort models in the world, but they basically all work the same. So there are small differences in the way they calculate, and there are small differences in the way the values they are produced. And the comfort model we are using here is the so-called PET, or physiological equivalent temperature. So this is basically a kind of felt, a kind of perceived temperature. So how do you feel in the outdoor environment, under the given conditions, with the wind, with the sun? So which indoor air temperature would correspond to this actual feeling I have right now? The good thing with PET is everyone can understand this. When I say it's a PET of 45 degrees, everyone understands that it's hot. When I say it's a PET of 20 degrees, or 21 degrees, like an in-room temperature, everyone understands, so it is more or less comfortable. So the main point when using the PET is also not to discuss is the 28 degree, is this really the boundary between comfortable and slightly warm, or is it 29 or is it 30? That doesn't make any sense because it depends also on people and history and so on. But the thing is we can use these PET values very good to compare the effects of changes by looking at the complete thermal complex with these 4 variables. So next slide, please. Thank you. So what you see here now, this is really a combination between the radiative effects, because you still see the shadow casting of the trees and of the buildings, but you can also see that there are other differences. These differences are caused by different air temperatures, and these differences are caused by different wind flow patterns. So these are the smaller differences. The big difference, of course, is always shade or not shade. And when we look at this situation, at this time it's 14 o'clock, so it's an hour later than before. In the shaded area, we have about 29 degrees centigrade. So according to the scale of PET, this would be between slightly warm and warm. So this is completely okay for summer, for an outdoor environment. So in the shade, it's fine. But in the sun areas, especially where the sun comes together with the wind, with areas with low wind speeds, you see it's going easily up to 45 degrees or even higher. So these are these areas which are pretty uncomfortable. So especially in the northern parts of the new built campus, for example, you see that there are quite hot areas that can establish. Okay, next slide. Thank you. So now we can go through that quite quickly. Sorry, I have to move this a bit. So this is the situation for 2050. So basically the patterns are of course similar because the wind flow is the same and also the solar radiation is the same. But of course the values, in this case it's the air temperature, of course, are much higher because we have 36 degrees now as the maximum temperature. And the effect of the park is more limited because due to the missing water, because the trees are running out of water now and they reduce the transpiration. And the transpiration is one of the 2 effects besides shadow casting that actually drives the cooling. And you also see the unshaded grass area are becoming to get a little bit of a problem because the grass was fine when there was enough water in the soil. But now as the soil gets dry and the grass gets drier, these grass areas can get pretty hot. So that's an issue we have to look after when we use grass as a tool for mitigation. Okay, next slide, please. Okay, but I think I will do that. Okay, I will go quickly through that. So this is the PET, and it's still basically the same conclusion. Everything is elevated a bit because the basic temperature is also a bit higher. Okay, next slide, please. So that's now what we suggested. So that's now fantasy. We have thought about the results of the plan, and we thought, what can we do to make an improvement to the situation? So what we actually did is we added a lot of trees along the main street. We added trees in the roundabouts. We added trees where there were some grass areas. So you see the red bubbles are the positions of the trees, so where they point to the trees. We also introduced some water elements, so that's the bubble number 4, so that we have some ponds along the building to use water cooling. And what we also did, this is the bubble number 6 and number 7, so that's the only thing which is maybe a bit hard to implement, but we gave it a try. We opened the building a bit, so we elevated it 5 meters higher so that we can pass through the buildings, and also not only people can pass through the buildings, but also the cooler air from the park can pass through that building so that it has a chance to flow over the complete area. Okay, next slide, please. Yeah, so now these are the redesign, the changes to the situations as we had before, compared to the planning scenario as it was before we applied our visions. You see, especially in the northern parts, for example, that the red bubbles have been removed. Also, the roundabout is a lot more cooler, and we had a lot of connection now between the park area and the eastern parts of the model domain. So if we go one slide further, thank you. So this is again the difference, because we cannot keep both pictures in mind at the same time. But you see here, what could we achieve in terms of air temperature with our new plan. Okay. So the blue values, these are actually the cooler areas. So we could reduce the air temperature by these redesigns by 1.5 Kelvin. This is quite a lot. These are the peak values. And for over large areas with this redesign area, we could reduce the air temperature 0.6 to 1 Kelvin over really large areas. Okay, so I think we can show one slide further. Then we have the PET. Simulation results 2050 for redesigned PET. Okay, thank you. Okay, so these are now the impacts and the changes of the PET. So of course we have more shading because we introduced more trees, and we also changed some of the materials. So we removed some of the asphalt where it was possible, and we have changed some of the water elements, of course. And if we go one slide further, thank you. Then this is the last one. You see again the differences in the PET. The differences in PET, of course, they are not that prominent like for the air temperature. This is because the PET is so sensible to solar radiation. And what you see here basically is the areas where we have now shadow casted from the trees, and basically from the trees, because this is the only element we have introduced that can throw shadow. All the other elements are not shadow throwing. So this is, of course, there are of course other changes in the PET of the air temperature, but they are much slower than this change of 15 degrees by the shading, so that you actually cannot really see them in the figure. Okay, so that was basically a very quick run through the ideas we had for the site d'escale, based on these 3 sets of simulation for 2017 and 2050, while the basic conclusion for 2017 and 2050 are of course the same. And I think it shows well that we have just added, I don't know, it was maybe 50 trees or so, and except of the changes in the building elevation, we did not do so many things. They are not very cost intensive, and they are not changing the infrastructure of the traffic or the housing infrastructure or whatever. But you still could achieve a reduction of 1.5 Kelvin or 1 Kelvin. And if you remember that the original plan caused an increase of 2 Kelvin and 2.5 Kelvin, you could turn back one of these 2.5 Kelvin and reduce it to 0.5 and 1 Kelvin, so that you still have a little change, a little increase due to the planning, but it's not that bad as it had been before. Okay, so thank you very much for your presentation and patience at the beginning.
Thank you very much. Next year, innovation will be a presentation in holograms. I hope everybody is ready. But anyway, do you have any questions? Actually, I have one, if I can start. Can you hear me?
Yes, I can hear you.
Perfect. So you've made a change in planting 50 more trees. So that's a good thing for all the ecological journey that's working at Vinci. But what about the buildings? Is there something that we can do also in the buildings just to cooling the area?
You mean what the effect is inside the building?
Yes, or on the structure.
Yeah, so that would be then a question for the building energy design people. So we have a very simple one-zone building model. So we can say what are the heat fluxes through the walls and the windows, and what energy input is inside the building. But it would make no sense to say this would reside in this and that air temperature in the different zones. So for that we would need an advanced building energy simulation model. But for that we can provide the boundary conditions then.
And what about trees on buildings?
This is an option. Trees on buildings, of course, are not always simple because of the wind loads, and also the benefits are then on the top of the building. So it's good for the people who have access to the rooftop, but it actually won't make a difference in the ground level.
Hello, Michael. This is Bruno. Thank you very much for presenting. And just to answer the question about the inside comfort, of course, the idea is then to combine the two assessments. So to start with the microclimate model and then to use the results of these models as boundary conditions to simulate the indoor conditions and then to be more detailed in the indoor model. I hope it is clear now. Okay.
Thank you very much for your presentation. Maybe as some more pragmatical feeling. I'm very interested on your works since I think that it can be applied quite immediately to our daily projects for zones around the Great Paris. And how can you imagine that the work you made on Cité Descartes can be scaled to other projects? I mean, is it something which is still a searcher program or something that can be, commercialized and applied on our daily projects?
No, this can. So we have a lot of customers who I don't know actually, so they just buy it off the box and they apply it to their projects. So this is a software which is usable as you can. So if you are familiar with CFD and some thermal models, it's very easy to go around with the software. So sometimes people ask for 2 hours or 3 hours training by Skype or so, and then they apply it to their projects. And it has already been applied, I don't know, worldwide to any kind of projects in the tropics, in Japan, in Australia, Norway. So it's working in the different climate zones. So if you go on the web page, which is going to be re-released today, so today is actually not working, but there are also a lot of cross-links to scientific literature who evaluate the model with measurements and so on. So these are actually research groups which are independent from us. So these are evaluation for different climate zones. So it shows that people are able to use the model without larger problems, and it doesn't function.
Any other questions?
I was wondering what is the range of calculation time depending on the size of the area you are modeling?
Depends on your computers. Well, actually with the next release we now have the option to make a parallel computation on the CPU. So this area I have just shown will need about 1 day of calculation time to simulate a 24-hour cycle. So it's more or less 1-to-1. But if you have a better PC, or if you have a larger area and a better PC, of course things scale up. It could be a week, or if it's a really, really large area, it could be 2 weeks. But if it's a small area, we just implement or just test your designs, it will be finished overnight. So it's really hard to say.
Okay, thank you very much for the presentation, although it was really hard.